All right, continuing our notes on electrons and energy. Right now we're focusing on the relationship between light and energy. As a substance is heated up, it emits light. That means it releases light. And Max Planck was the person who studied this phenomenon and related the energy to the frequency and wavelength of electromagnetic radiation. So here's an example of what he was studying. If you heat up a piece of iron, so iron before you heat it, it just looks dark gray at room temperature. But it glows red when it's heated enough. And then if you heat it just hot enough, even higher temperatures, you get a blue color. Well, Max Planck studied that phenomenon, and it led him to conclude that matter can gain or lose energy only in small specific amounts, and he called those quanta. Okay, a quanta or quantum is a small amount of energy. It's a very specific small amount of energy. You're going to need to know that word when we get to the lab. All right, a quantum is the minimum amount of energy that can be gained or lost by an atom. So then he came up with this equation, or it's credited to him at least, the relationship between energy and frequency. And we have this thing called Planck's constant, which is 6.626 times 10 to the negative 34th. You don't have to memorize that. We're going to give that to you. But just be aware, anytime you see h, that is a constant. It's always going to be the same number, just like the speed of light. Remember in our last equation, I'm going to scroll back up to the last page. The speed of light is always 3 times 10 to the 8th meters per second. Planck's constant is always 6.626 times 10 to the negative 34th joules per second. And that's important because it comes into how we're going to be solving these problems. E is energy, and the unit we're going to use is joules. We use a capital J to represent it. F stands for frequency. We've already seen frequency, and its units are always going to be hertz or inverse seconds. Remember, sometimes we write inverse seconds as just s to the minus 1. Now let's do our first example problem. Tiny water drops in the air disperse white light of the sun into a rainbow. What is the energy of a photon from the violet portion of the rainbow if it has a frequency of 7.23 times 10 to the 14th inverse seconds? Now, I told you it was frequency, but even if I didn't, you should know its frequency because the units of frequency are inverse seconds or hertz. All right, so we've got this equation, E equals HF. That's what we want to know, is what's the energy. So let's write down E equals we don't know what that is. That's what I'm looking for. H is always Planck's constant. It's always 6.626 times 10 to the negative 34th, and we've got these weird units called joule seconds. Don't worry too much about that. Just know that's going to help us to determine what the final units are. So E equals H, and then we've got F, which stands for frequency. The frequency is given here as 7.23 times 10 to the 14th inverse seconds. Okay, so just know that seconds and inverse seconds are going to cancel each other out. They're going to go away. And what we will be left with in the end is energy units that come from this. Energy units of joules, to be exact. So our energy is going to be in joules. Now let's set it up and solve the equation. E equals H times F. So that's 6.626 times 10 to the negative 34th. That's H times F. So we're going to multiply by 7.23 times 10 to the 14th. And when you multiply those together, you're going to get your answer. Let's pull up our calculator and try it out. Remember, we're going to use that E button anytime you see scientific notation. So 6.626 second, comma, negative 34. And then I'm going to multiply 7.23 second, comma, that gives me the E 14, and hit enter. I get 4.79058, blah, blah, blah. Okay. I want to round it to the same number of sig figs as the least number of sig figs in the problem. So I need to have 3 sig figs in my answer. 4.79 times 10 to the negative 19th. Don't forget to always look for that E. 4.79 times 10 to the negative 19th. And our units for energy again are going to be joules. Capital J. All right, that's it for exercise 3, which is our first example involving this equation. Now let's look at number 4. This one's a little more involved, so stay with me. We need to think through, and in chemistry there's a lot of problem solving that you're going to do. Same thing with physics, a lot of problem solving, and especially if you go into AP chemistry or AP or on-ramps physics. So we need to think not only about what we're trying to solve, but how do we get there? So it tells me the blue color in fireworks is often achieved by heating copper chloride to about 1200 degrees Celsius. Well, that's a number, but I haven't even talked to you about any reason that we would use that, so we could actually cross that out. It's probably a distractor. Then the compound emits blue light having a wavelength of 450 nanometers. There's that word wavelength. Okay, we talked about wavelength. What's the increment of energy with a quantum that is emitted? Really, I'm asking for the energy. What's the energy that is emitted at 450 nanometers? So same number, same units at 450 nanometers by CuCl2 or CuCl. And it reminds us that 1 nanometer equals 10 to the negative 9th meters. All right. I'm looking for energy. So our equation for energy is E equals HF, right? All right. And H we said is 6.626 times 10 to the negative 34th joules seconds. Joules times seconds. All right. Here's the problem. I don't have frequency. I have wavelength. So how could I even solve this problem? Well, I'm going to have to use the other equation. Remember on the last page? We know how to find frequency if I have wavelength, so I'm going to use that. So this is a problem where we're going to use both equations because I don't have frequency. I'm looking for this, but I don't have this. So the way that I would set this up is draw a line right there, and I'm going to solve another problem down here. C equals wavelength and frequency. Frequency is what I don't know, and whenever I find that, I'm going to put it up there, and then I can solve my problem. Okay, so whenever I find my wavelength, or whenever I find my frequency, I'm going to put it up there. My wavelength is given to me. That's 450 nanometers which is 450 times 10 to the negative 9th meters, right? Or you could say 4.50 times 10 to the negative 7th if you put it in the calculator, but I wouldn't worry about it. We're just going to plug it into the calculator like that. And then C is always the same number, and we can go back up to our notes if we need to check. On the first page, C is always this number up here, 3 times 10 to the 8th meters per second. 3.00 times 10 to the 8th meters per second. And my frequency needs to be in units of inverse seconds or hertz. Either way. All right, let's go ahead and solve this now. So I have 3.00 times 10 to the 8th equals, remember C equals wavelength times frequency. That's what we're doing down here, and we're trying to find frequency. So 3.00 times 10 to the 8th equals, the wavelength is 450 times 10 to the negative 9th, or we could do 450 e negative 9 in the calculator, and then that is multiplied by f. I want to solve for f, so I'm going to divide both sides by 450 times 10 to the negative 9th. Just algebra. Just doing some algebra here. So f equals, when I put that in my calculator, 3.00 times 10 to the 8th. Use that second comma. 8 over 450 second comma negative 9. I get 6.67, or in this case I actually just want two significant figures. So 6.7 times 10 to the 14th inverse seconds, or you could say hertz. Either way, but that's the frequency. Remember to look back at your question. Is that what I'm looking for? It's not. So I'm going to take that number and I'm going to move it up here. So I'm going to take this 6.7 times 10 to the 14th, and we're going to move it up here so that I can solve for my energy. Okay, so my frequency is 6.7 times 10 to the 14th. Now I want to solve for energy, and E equals H times F. So E equals, now I have H as 6.626 times 10 to the negative 34th. And multiply that by frequency, which is 6.7 times 10 to the 14th. Energy equals, let's put it in the calculator, 6.626 second comma negative 34 times 6.7 second comma 14, and I get 4.44, or just 4.4 to give me two sig figs. 4.4, don't forget to check the end, times 10 to the negative 19. 4.4 times 10 to the negative 19. Make sure you try some of these out on your own so you make sure that you end up with the same numbers in your calculator. And again, the seconds and the inverse seconds cancel out so that I end up with joules as my energy units. More importantly, you could just kind of look up here and remember that the units of energy are going to be joules. Units of energy are joules. Units of frequency are hertz or inverse seconds. You can write it as s to the negative 1. And the units of wavelength are going to be either meters or nanometers. All right, so that's it for our notes on electrons and energy. There's some practice. Make sure you finish out that practice. We're going to do a lab next class that involves some of the information from the first couple pages of these notes along with some calculation practice.